Hello everyone, thank you for attending today's presentation on the Pennsylvania Flex Beam. I'm Mark Nicholson. I'm the District Bridge Engineer for PennDOT's District 1, which encompasses the 6 counties in the northwest corner of Pennsylvania, including Erie, Crawford, Mercer, Warren, Forest, and Venango counties. For today's presentation, I'll be covering 5 main topics: what is a flex beam, what it is composed of, and how it functions. Why did we develop the flex beam, and where do we intend on using it? And I'll go into detail on our pilot project, which we just completed this past summer in Erie County on State Route 3010. I'll provide a brief overview of the design and the scope of the project. I'll highlight key parts of the fabrication project, and I'll walk you through some photos showing the sequence of construction and the final product. So what is a flex beam? A flex beam is a modular system that consists of a precast concrete deck and a steel stringer. But what's unique is that unlike traditional steel beams, the flex beam does not include a top flange. In other words, the top half of the I-beam. So it looks more like an inverted or an upside down T. This makes a more efficient use of bridge materials by not including the top steel flange and the compression zone where concrete functions at its best. Other benefits of the flex beam is the deck panel is precast in a shop environment where weather is not a factor and it's easier to maintain quality control. Having the deck panel precast also saves time on the construction site, which reduces detour duration and inconveniences to the traveling public. The photo on the left is a test panel that was built and tested by Lehigh University. The diagram below is from PennDOT standard drawings for flex beams. These standards were largely based on the testing and development done by Lehigh, and they can be found in the PennDOT standards under BC 663. A key point of this diagram to note is the holes in the top portion of the beam web. These holes allow for reinforcing steel to provide the shear interaction between the beam and the concrete deck. This will be better illustrated later in the presentation with some photographs. Moving down on our list of topics, we're now going to answer the question of why do we need a flex beam and where would we be using it? Our previous district bridge engineer, Bill Kohler, used PennDOT County bridge crews to build precast concrete channel beams and perform bridge superstructure replacements. The problems Bill started to run into was that the county crews had limited equipment and were limited to a span length of about 35 feet due to the weight of the concrete beams. There's obviously many single span bridges greater than 35 feet that are in need of replacement, and Bill was looking for a beam option that was lighter and would allow the county bridge crews to continue with their replacement program of bridges of longer spans. You can see on the diagram of the left the precast channel beam detail that was being used, and the photo at the bottom is an example of a completed channel beam bridge being viewed from the underside. Okay, so now we're ready to discuss our pilot project. The photo on the left is a photo of the existing bridge. As you can see, it's in a rural area with a relatively low ADT. We felt this was an ideal location since this was an innovation project and would allow ease of monitoring and inspection. And if there were performance issues with the bridge, it was not on a critical part of our network. The existing bridge was built in 1956, had a span of 32 feet. The curb-to-curb width was 22 feet and was supported by 6 steel stringers with a depth of 24 inches. The scope of the bridge was a superstructure replacement. For those of you with PennDOT ECMS access, the number is 97126. The project was let in June of 2020. The original contract value of the project was $593,000 roughly. If you separated the bridge costs out, that totaled about $365,000, which equated to a rough unit price of about $438 per square foot of deck area. The new design included the same span of 32 feet with a slightly wider curb-to-curb width of 23 feet. This required 5 flex beam modules as shown on the typical cross section to the left. In between the modules, ultra high performance concrete was used in closure pours to complete the deck system. Lastly, after completion of the beam setting and closure pours, a waterproof membrane and bituminous overlay was placed on the bridge deck. Next, we'll talk about fabrication process for the project. First, steel beams were comprised of welded steel plate girders. In the photo of the left, you can see one of the actual beams that was used on the project. You can note that the web holes that we discussed earlier and that allow for the shear connection to the concrete deck in the top portion of that web. It's also worth mentioning that we specified a 50 CR steel, which is a stainless steel for this particular project. It's not a requirement of the flex beam design. We were just looking for an active project that we could try specialized steel, and this happened to be the right project at the right time. After the stringers were fabricated, they were shipped to a precast facility for the addition of the concrete deck panel. The photo on the left is a progress photo showing the formwork and rebar installation. As part of the shop drawing development process, the fabricator developed a 3D model of the rebar cage to check for interference and conflicts, both within the module and also the adjacent modules. The images below shows an example of the model and the module details taken from the contract drawings. This proved to be a valuable exercise as they did discover a few minor conflicts. Thankfully, only minor adjustments were needed to resolve the conflicts. However, without this model, there could have been more serious issues in the field when they tried to set the modules in place. This slide is just providing a photo of a completed flex beam module that's ready for delivery to the job site. Now we're into the construction phase. As I stated before, the scope of the project was to replace the superstructure of the bridge. The photo on the left shows the existing bridge deck and beams being removed, and the new abutment caps and beam seats are ready for the flex beam setting. In the photo below, you'll notice that anchor bolts were installed in the flex beams prior to the beam setting, and that had to be done due to unavailable access from above from having the deck and diaphragms precast. These are just a few photos showing the flex beam setting operations. In the photo to the right, you'll see why it's important to check for rebar conflicts. Overall, just because of the amount of rebar between the two adjoining flex beam modules, overall beam setting went very well on this project. There were no issues and everything fit together very well. As mentioned before, we used ultra high performance concrete in the closure pours. As you can see in the photo on the left, the rebar is tightly spaced, and that just reiterates the importance and advantages of using that 3D modeling to check the rebar clearances. The ultra high performance concrete is batch mixed on site, so there's a fair amount of labor involved in mixing and transporting by wheelbarrow. Some of the engineers attending may be wondering how we can get away with such short rebar and a joint like that. The ultra high performance concrete has a compressive strength of over 20 KSI, so the development length can be much shorter as compared to using a traditional concrete mix design. These are a few photos showing the completed project. The photo on the left shows the full cross section from underside the bridge, and on the right you can see how the UHPC or ultra high performance concrete closure pour turned out in that close-up photo. These are some more photos of the completed project. The view on the left is similar to the one that I showed you on the first slide, just a closer view. You can notice how shallow the beams appear relative to the deck and barrier. That comes from the close beam spacing, number of beams, and economizing of the beam design. The photo on the right just shows a close-up of the new cheek wall and abutment work that was done. Now we're ready to talk about some lessons learned. First, with the ultra-high performance concrete closure pours, our plans did not specify the textured finish on the diaphragms. The contractor did do some texturing in the field with hand tools, but would have been much better product had the plans required the diaphragm to be textured. As I mentioned before, the 3D modeling done by the fabricator proved to be very valuable to check for rebar conflicts and is something that you might want to consider for your contract documents. Specifically for the CR50 steel, during fabrication we learned that the material availability can be an issue since it's not a common, more readily available material. Stringers were fabricated in accordance with the plans, but we had to use carbon steel for sole plates because the CR50 size that we needed was not available. There's also differences in the fabrication and testing requirements for stainless steel as compared to carbon steel. I'm not going to dive into those details due to time constraints. However, if anyone would like more information on that, feel free to contact. The photo to the left is a view of the bridge completed from standing on the roadway, obviously. But I'd just like to close out today's presentation by discussing our future plans for the flex beam. We're in the process of installing gauges that will monitor live load effects on the flex beams. The gauges aren't installed yet. We're still working on the contract to get those services in place, but we hope to have that worked out soon. One of the surprising advantages that we learned about the flex beam is the speed in which it was constructed on site. The total time to complete the project was only 6 weeks, and according to our inspectors, the actual superstructure portion only took about 4 weeks. This obviously would be a good option when you're looking for an accelerated bridge construction project. Lastly, a word of advice is just to make sure you allow sufficient time for fabrication when you're planning your project. As you saw earlier, for this project, the stringers were fabricated in one shop and shipped to another for the precast work. This obviously requires time for separate handling and delivery, so that needs to be accounted for in your schedule. That concludes today's presentation. Thank you for attending, and I hope that you found this informative and maybe you'll have a project to consider a PA flex beam for in the future.
Good day. My name is Nick Vivian. I'm the Hydrology and Hydraulic Unit Manager in the Bureau of Project Delivery, Environmental Policy and Development section. It's my pleasure to present to you an update on the topic of change, which is an acronym for Collaborative Hydraulics, Advancing to the Next Generation of Engineering. Change came from the Everyday Counts initiative sponsored by the FHWA. Everyday Counts is where the FHWA, state and local transportation agencies collaborate and select underutilized innovations to promote. This particular innovation was unique. It was chosen from more than one EDC session. EDC 4 in 2017-2018, and again for EDC 5 in 2019 and 2020. Through this initiative, FHWA has encouraged each state to shift from one-dimensional hydraulic modeling to two-dimensional hydraulic modeling. They encourage the use of the SRH 2D program by providing funding and technical support to the states to make this transition easier. The diagrams below show the progress across the United States from January of 2019 to December of 2020. As you can see, Pennsylvania has progressed from the demonstration stage to the assessment stage in that time frame. Currently, we are in the process of institutionalizing 2D modeling, and with the upcoming Design Manual 2 rewrite, there will be conditions where 2D hydraulic modeling will be required. A quick review of 1D versus 2D modeling. One-dimensional hydraulic modeling forced designers to make assumptions about stream flow and potential flooding impacts. Calculations are averaged across each cross-section with gaps in between. 2D hydraulic modeling is a finite element analysis where a 3D surface mesh is generated and vectors are calculated at the center of mass of each 3D element. The flow directions are calculated, not assumed. The best way to represent the difference between 1D and 2D modeling is through artwork. Artwork, as shown on the current slide for 1D dimensional modeling, shows a one-dimensional model as a stick figure, very crude, representing assumed cross sections with gaps in between, versus a very detailed, finite 3D mesh represented by a fully detailed three-dimensional photograph. This gives the users a clear representation of the difference between 1D and two-dimensional modeling. How is direction calculated? Well, the velocity is a vector data set with components in the x and y direction. Ineffective flow areas are calculated and are no longer assumed. Obstructions are directly modeled in the mesh with actual field survey vertical elevations built into the surface mesh with break lines. Overtopping is easily determined by the advanced graphics. This slide shows a list of bullets that are some of the complex hydraulic challenges that 2D modeling helps solve. The most common found on PennDOT projects are highly sinuous channels, multiple openings, multiple structures with split flow, confluences, or multiple channels. Using 2D modeling, designers can see stream flows and velocities around bridge structures and the potential impacts on the surrounding area by the advanced graphics. Thousands of elements are shown representing hydraulic flow and floodplain geometry. The graphic to the right gives the user the visualization needed to see what is going on hydraulically. As you can see, the flow is represented by vector arrows, and that diagram shows the complex challenges seen on PennDOT projects. You can see multiple openings and confluences, all color-coded graphics to represent velocity. Two-dimensional modeling enables more accurate designs of bridge openings, span arrangements, roadway profiles, scour countermeasures, and bank protection. The graphic to the left shows spots of high velocity to provide a more accurate scour countermeasure design. As you can see, the area shaded in red shows velocity up to 10 feet per second. The latest version includes enhancement tools for 2D floodplain and floodplain analysis. The graphic to the right shows a more detailed floodplain due to the finite element vectors that represent the 3D surface mesh instead of the average elevations and gaps between cross sections of a 1D model. With the graphic to the right, the finite element analysis fills in those gaps that's missing in a 1D model to get a more definitive floodplain. 2D modeling provides better tools for communicating interactions between waterways, the transportation network, and the environment. It allows for a more streamlined project development approach, and it improves the ability to design safer, more cost-effective, and resilient structure over our waterways. To institutionalize this innovation, each district was required to do at least one 2D model for 2021. The Bureau of Project Delivery H&H unit was to assist each of the 11 districts in selecting and developing one project each. Progress was affected with the COVID-19 pandemic due to the transition of remote working over VPN, travel restrictions, the complicated training, and a CAD update from En-ROADS to OpenRoads Designer. Currently, to date, there are 4 districts that have selected projects and are either in design, ready to submit, or are authorized. I would like to present District 11 and District 1 project. Other districts will continue to develop their models this year. District 11's 2D model. District 11 chose State Route 65, Section B34, the Mercer Road Bridge Replacement Project. It's located in North Swickley Township, Beaver County. This graphic represents the existing and proposed 100-year event, 2D flow elevations. We left in the 3D surface mesh elements into the graphic so you can see the limits of the model. This graphic also shows the overtopping being eliminated. The next slide shows a graphic that represents the existing and proposed 100-year 2D velocity vectors. As you can see by this graphic, the velocities are reduced. The graphic to the left shows an area in red below the culvert of high velocities. The graphic to the right shows the new structure with the red velocity hotspot eliminated. This slide represents the deliverable to the funded reviewer. As you can see, the existing and proposed floodplain are color-coded and shown on one map, as well as the existing and proposed water surface elevations. They're plotted from the calculations, and they look more like contours, which represents more real-world conditions. What this does is streamline the review process by allowing all the informative detail the funded position people review to be on one plan sheet rather than flip back and forth between multiple sheets and multiple reports of a 1D model. I'd like to talk about District 1 2D model. District 1 shows State Route 4007, section DF1, which is over the tributary to Little Broken Straw Creek in Bear Lake Borough, Warren County. The red dot in the picture represents the location of the culvert. This slide really shows the benefit of the 2D model and the advanced graphics, especially when you consider how you would have modeled this and drawn cross-sections if you were using a 1D RAS model. The 3D surface mesh of the 2D model show the flow between the house and the garage, and that it is mitigated by the larger structure and upsized cross culvert. The graphic to the left shows the existing conditions of the 10-year event, where it's impacting the home and the garage. The graphic to the right shows that the proposed structure mitigates that risk to that property. One of the things that came to our attention during the review process, and one of the points that I wanted to make with the 2D modeling, having more detailed computations and enhanced graphics, is that it reveals more detail and uncovers some unexpected design impacts. The graphic to the right reveals an increase in velocity downstream of the culvert and adjacent to the garage structure. This increase was commented on in the review process, and the program tools were used to evaluate this increase and prove that risk to the stream bank was not triggered. This slide shows the tools available in the 2D model to do a further in-depth analysis of velocity increase adjacent to the garage. As you can see with the diagram on the right, reference lines were drawn and plotted to prove that the velocity increase was isolated to the main channel instead of the stream bank. These advanced tools allowed clear, concise information to be transferred, and analysis to be done, and to prove that velocity increases did not affect stream bank erosion. This slide again shows the deliverable to the funded reviewer, where everything, all the pertinent detail is put onto one plan. The existing and proposed floodplains are color-coded. The existing and proposed water surface elevations are calculated and plotted, and again represent more real-world conditions. This allows for a streamlined review process and to speed up the review times. This concludes the presentation, and I will now address any questions you may have.
Hello, my name is Matt McSweeney. I work for PennDOT's Structural Materials section, part of Bridge Design and Technology. I'm here today to discuss precast, prefabricated bridge elements and materials, more specifically the express foundation systems designed by Contec. Here's just a general overview of our agenda. We're going to discuss typical construction project issues, benefits of precast concrete foundation systems, Contec's express foundation system, and field installation photos. And then we're going to review some system design issues, and I'm going to provide a little bit of commentary. So typical construction project issues that we tend to see are that we have lengthy demolition times extra time required for excavation, form setup, concrete placement, concrete curing, and concrete strength development. This can cause impacts to roadway users, basically causing lengthy construction schedules and other delays. That brings us to express foundation systems. We have different methods that we can employ in order to speed up construction. One of those items is express foundation systems. Basically, the benefits of a precast concrete foundation system will speed up construction, limit the size of trench excavation, limit roadway closures because we can install the pieces, backfill them, and then open the road and return it to service. There's no waiting for extended cure times and cast in place concrete. And the elements are typically cast indoors, and we can control the environment during casting. And as a result, we tend to see higher strength concrete than field cured concrete. Some of the negatives are that it requires large equipment to place large or heavy elements. Then we can limit site and space constraints. We also have oversized and overweight trucking. Sometimes these elements can be quite sizable, and as a result, we have to have permitted loads. However, sometimes we can limit the piece weight individually and deliver those pieces on multiple trucks. So that leads into our express foundation system or modular foundation system. Essentially, we take lots of little pieces and we assemble them into one element. So we'll talk about Context Express foundation system. Here you just see a general layout or a general detail that basically shows modular units for the foundation. So as you can see here, what we actually have is a cross-section of the footer and a aerial view of the footer. And essentially this area right here is a void space that then gets cast with concrete out in the field, and it could be an accelerated casting. Here we have another cross-section of our foundation system, and typically what we see is this be used with a arch structure, and as such you see the keyway. These holes here are meant to have reinforcing bars fed through them, and essentially if you took a look at our previous slide, essentially those rebar will extend through the cast in place portion of the foundation system. As I said, these are used in concert with an arch section. Typically, they can be very sizable elements, but all of these elements could be delivered more or less around the same time. So as you can see here, we've got the arch system along with a cast in place pedestal and then the footing. Now typically we may or may not see a pedestal system, and in fact one of the projects that I'll be presenting later did not use a pedestal. So the benefits of Context Express foundation system is that it allows for work on sites with limited room or access. We can utilize smaller equipment in order to lift the material or lift the foundation systems into place. As such, we can utilize smaller trucks and smaller cranes in order to erect the pieces. Typically, they're easier to handle and orient than larger elements, and they can be oriented in small excavated areas. Large pieces can be used since they are made with voids, so we can cover a larger footprint, and as such we can use that to place those pieces in the field and fill those void space with an accelerated concrete. They can be easy to assemble. and it can be used for short excavation sites, areas where you really do have a limited excavation limit. We can use grout, concrete, or UHPC for the closure pour. So here I'm going to discuss a site installation that was performed in Perry County. This is Laurel Run Road over Laurel Run. Essentially what we had done is the road was not detoured, but a temporary excavation was put up. A temporary relocation of the road was installed in order to erect this structure. So here you can see some of the elements, in fact, 2 of the foundation elements being delivered on truck. As discussed, bundles of reinforcing bar fed through those blockout areas, and these can come pre-installed. That way, all you have to do is pick the piece and set it into place. As you can see here, we've got the element being erected into place. Just another view of the erection. Now these items can be used, put on mud slabs, they can be placed on shim packs, they can be placed on a stone base. Essentially anything that we can get a nice level position to place these foundation systems. As you can see here, we utilize a level in order to assure that we've got the correct alignment and slope of the piece. Here we can see the second element being put into place. Now this is going to form the main abutment portion, or the main foundation portion for the arch culvert. Just another view. Now we're bringing in the wing wall portions of the foundation system. The arch culvert's wing walls will sit on top of these foundations, and as you can see, there's some small pieces, and essentially what occurs is that the reinforcing bar will extend through this foundation system and into this void space in the wing wall portion, as you can see by this angle here. Overall, this is kind of just the outline or placement of the piece. And here's just another angle and the other abutment. As you can see, we've got both foundation pieces installed. In this photo, you can see this is after the void spaces have been filled in with a structural concrete mix. This mix, I believe they flooded the foundation after casting and setting in order to help cure the piece. As a result, you can see that it's been cured out, and they have the angle pieces in order to attach the arch culvert to the foundation. In this view, you can see the arch culvert being set on top of the foundation system. As we continue through the excavation and through the placement. So I just want to discuss a few items regarding this express foundation system. We did encounter a few issues along the way, and I just had some comments for items that we need to be on the lookout for. The abutment, footing, and wing wall alignment details are quite critical. It's important to assure that we've got the subgrade graded and the elevation is correct. We can use stone or mud slabs. The use of shim packs can be quite cumbersome in order to get it just right. And the sections need to be sized appropriately for site conditions. This site condition we actually had utilities on one side of the structure. Therefore, swinging and transporting was quite limited to one location. The crane pad had to be set up on one side of the abutment, and it precluded a way for the trucks to actually pull through the job site in order to easily offload the pieces. And then the top of the foundation, it wasn't quite level, and the arch made it difficult for the actual placement of the pieces. Kind of discussed also in the previous discussion, it made it difficult for the riprap to be placed. So as you can see here in this detail, we see that the foundation shall bear on Class C concrete, mud slab or leveling pad, or use of shim packs. As such, it's always best to probably pour a mud slab in order to make sure that we've got a nice level foundation. One of the other issues that we kind of ran into was actually aligning this foundation, or this wing wall foundation, with the actual arch foundation. This detail kind of made it a little cumbersome in order to get pieces lined up just right. There's actually dimensions from this front corner forward and backward that required a lot of adjustment and moving of that wing wall piece. As you can see here, it might have been better to line up this piece quite parallel with the main foundation of the arch culvert. As you can see here, some of the other details that we've seen, just details showing that the alignment of the wing wall and the foundation, the express footing foundation with the arch culvert, kind of doesn't line up nice. It might have been better to square this piece off. So as you can see here in this photo, this dimension here is 3 3/8. So we just got to be cognizant of the dimensions that we're speccing. 3 3/8 might be a little more difficult to kind of move these pieces around. It might have been better to call out 3 inches or 4 inches or 3.5 inches, just to make things a little bit nicer and easier for placement out in the field. As you can see here, forward and backward, that piece can kind of vary quite significantly. So as previously discussed, this is probably a more appropriate way to align it. Given that these are precast footers, we can better accommodate this geometry out in the plant rather than out in the field. So it might be better to kind of just align these items so that they're square, so that when we're placing them in the field, there's no thinking about it, really no measurements. All we have to do is drop it into place, align it, and move on. So as previously discussed, placing these culverts and then the clearances in order to place riprap and place other materials in order to spread it out. We've got very limited clearance, as you can see here, by the causeway barrier, as well as underneath the arch. Made it really difficult to actually spread that riprap, and realistically we want to be cognizant of that and make sure that we're not impeding the ability to properly place the material underneath the culvert. As you can see, just another angle for how significantly close we were with the causeway barrier. So again, my name is Matt McSweeney. I work for Structural Materials section in PennDOT, and I cover the eastern region of Pennsylvania. My counterpart in the western region is Randy Lazarus, and here's our contact information. If you guys have any questions, feel free to reach out. Thank you and have a great day.
Good morning. My name is Jeff Stryker with STV. I'm a Vice President and Engineering Director for Project Delivery. Today I'm going to be presenting curved tubular flange girders, which were implemented on the I-95 Section BR2 project for the Ramp B over Conrail structure. Before we talk about the I-95 Section BR2 project, wanted to talk a little bit about tubular flange girders in Pennsylvania. The original concept was developed in 1990s at Lehigh University by Wasef, Sauce, and Fisher, where they participated in an FHWA and PennDOT research project for concrete-filled tubular flange girders. The first demonstration project was completed in District 1, designed by Michael Baker, and was a 2-span tubular flange girder filled with concrete. The second tubular flange girder demonstration project was in District 6 and is on the I-95 corridor and is the first curved tubular flange girder in Pennsylvania. Types of tubular flange girders are shown below, with either concrete filled or hollow tubes. As you can see on the two tubes sections on the left, concrete is used to fill the top flange of the tubular flange girder for additional compressive strength and can be either a square tube or a circular tube. The two sections on the right show hollow tubular flange girders with rectangular tubes on both the top flange and on the bottom flange. Curved tubular flange girders were developed in 2014 when a test bridge was constructed by Lehigh University. Research findings by Mott and South in 2015 and 18 found that concrete infill was not required and resulted in a lighter section. They also found that a tubular flange girder with only a tubular top flange had similar response in curved applications compared to a tubular flange girder with both a top and bottom flange with both a tube for a top and bottom flange, and did not require cover plates for longer spans. The picture below shows the curved tubular flange test bridge constructed at Lehigh University for the testing in 2014. Some advantages of tubular flange girders to the traditional I-girder include increased torsional stiffness and strength, as well as additional lateral torsional stability of the girder section. They also provide a potential to reduce the number of diaphragms and cross frames within the framing plan, as well as reduce web slenderness because of the larger top flange resulting in a smaller web. There's also less temporary support needed during construction, where only the ends need to be braced. I'm now going to talk about the I-95 Betsy Ross Interchange project, where tubular flange girders were used for a curved ramp structure within the interchange. I-95 Section BR2, which is the second phase of the interchange reconstruction, was let in December of 2019 for a low bid of $93.6 million, which was within 1.5% of the design estimate. The contractor is Buckley and Company, and the structure using the tubular flange girders, Ramp B over Conrail, had a lump sum cost of $4.1 million, and the fabricator is High Steel, the tube bender is Chicago Metal Products, and the project is supposed to be completed at the end of 2022. Ramp B over Conrail had a number of site constraints that warranted consideration of tubular flange girders, including crossing over Conrail and New Jersey Transit, as well as spanning underneath Amtrak and PECO transmission lines, as well as being adjacent to a number of existing and proposed structures, as well as Frankfort Creek. Constructability concerns at the site included restricted crane operations and clearances, coordination for track outages with the railroads, coordination with transmission line outages for PECO, including national grid coordination, beam delivery to the site, limited staging area demolition of the existing structure, and maintaining traffic on the adjacent ramp. A little bit more information about the ramp B over Conrail structure. It's a simply supported 148-foot span with a 530-foot radius. Girder radii vary from around 520 feet to over 550 feet. The girder section comprises of a 20 by 12 rectangular structural steel tube section, top flange, with a 65-inch web and a 24 by 2 3/4 steel plate for the bottom flange. The material used in construction of the I-girder is the tube is made of ASTM A500 grade C 50 KSI steel, and the plates are standard ASTM A709 grade 50 steel. Below is a typical section of the structure, which carries a 39-foot curb-to-curb cartway, resulting in a 42 4.5-inch out-to-out width with 5 girders spaced at 8'6". Below is the proposed framing plan for the bridge, which includes 2 skewed supports which parallel the Conrail and New Jersey Transit tracks, and includes 4 intermediate diaphragms for each girder and skewed diaphragms at the supports. There are 2 different diaphragms on the structure. The intermediate diaphragms are traditional K-frame diaphragms, and the end diaphragms are full depth steel I-girder sections. Things to consider during design. There are limited fabricators that bend large tube sections, so you want to make sure that you're choosing a tube size that is available or that fabricators can bend easily. Additional fabrication costs should be considered associated with the tube bending and fabrication. Detailing for field splices are also difficult, particularly when using larger spans or continuous girders. For the ramp B structure, an initially designed field splice was eliminated based on further research into shipping routes or shipping availability of a longer span. Sealing and drainage of the tube should be considered to minimize moisture inside the tube, and inspection techniques for the tube should also be considered. There are a number of things to consider during fabrications. You want to make sure to specify an AISC qualified bender roller and that all the tube material is from the same lot or heat number. We only used cold bending during the fabrication of ramp B over Conrail and specified that a mandrel be used and have a firm slip fit. You should also include limits for post-bending distortions in your specifications. You should also define the location of the tube's weld seam. Ideally, the weld seam should not be on the same side of the tube, on the inside of the bend radius, and near the neutral axis of the rectangular tube. You should also monitor stiffener fit to reduce gaps between the stiffeners and the tube for welding. Construction considerations for curved tubular flange girders, particularly when used on restricted sites, is that special rigging may be required when you have restricted crane operations. Tie downs and keeper bars can be used for stability during a pick, particularly with girders with tight radii. For the BR2 project, a test lift was performed prior to field erection given the tight site constraints. For more information on the I-95 corridor project, please visit the I-95 Revive website at i95revive.com or follow the project on Twitter at I95info. Thank you, and I'll take any questions.
Hello, my name is Carson Carney, and I am the Vice President of Technology Integration for Advanced Construction Robotics. I appreciate the opportunity to talk today about real-life examples of bringing robots to construction job sites that started right here in Pennsylvania. I will be talking to you today about two specific single-task construction robots. The first robot is called TieBot. TieBot is intended to work as a piece of equipment with the existing rebar crews. Now, it's a construction robot, so it's a very smart piece of equipment with autonomous features that allow it to self-locate and self-tie the rebar intersections on bridge decks or other horizontal rebar applications. It performs the bulk tie or pattern tie activity associated with the horizontal deck rebar. It doesn't require any input like BIM models or even rebar spacing. As you can see, it's deployed on a gantry truss, much like the Bidwell paving machines, and runs on the same screed rails. TieBot was developed in conjunction with and was conceptualized from Steve Muck, the owner of Southwest Pennsylvania general contractor Brayman Construction Corporation. The next construction robot is called IronBot. Like TieBot, it is a gantry deployed solution that runs on screed rails and lifts, carries, and places the horizontal rebar ahead of the TieBot. IronBot again is intended to work with and interact with the human rebar crew to reduce the heavy lifting and strain that comes along with placing the rebar. As mentioned, Brayman Construction was constantly encountering issues on their projects relating to rebar installation. The challenges are ever present on projects with bridge deck rebar. It is typically a critical path activity that most often occurs during peak season, where labor shortages are common. The process also typically occupies a significant portion of time on a project schedule. Workers dislike the task as it falls into the 3 Ds category of being dangerous, dull, and dirty. One major challenge is that rebar labor is often rebalanced or reallocated to different projects due to the lack of labor and pressure to keep good skilled people working. How many times have you seen a deck with a crush of workers on it one day to almost no labor out on the next? All of these challenges often result in project delays that can have severe penalties associated with them. TieBot started commercial deployments in May of 2018. Since then, it has been on over 30 projects and placed around 2.1 million ties on over 7.5 million pounds of rebar, with 0 lost hours. 13 of the projects have been right here in Pennsylvania, including the Koppel Bridge, CSVT, Orrs Bridge, Betsy Ross, and the Southern Beltway. This shows just a snapshot of some of the contractors that are gaining speed and efficiency by augmenting their rebar crews with robotics. We performed a detailed case study on the Koppel Bridge, which is located about 40 miles from Pittsburgh. This project is a 4-span bridge with a 43-foot wide and 1,240-foot long deck. Brayman Construction Corporation was the general contractor, and it was completed in October of 2019. TieBot was brought out to perform the bulk tie activity on the horizontal bridge deck rebar. There were 535,000 pounds and 250,500 ties on the roughly 53,000 square foot deck. Prior to measuring the impact the robots have on the labor, we first benchlined how much time the crews typically spend on the activities that have potential to be automated in the future. We studied the Koppel Bridge crew and another crew that worked on the 9th Street Bridge in Pittsburgh. We found the Koppel crew expended 20% of their man hours on the bulk tie process that TieBot was intended to perform, and 27% of their man hours on the carry in place activity that IronBot will eventually perform. So overall, 47% of the man hours had potential to be impacted by the robotic solutions. When TieBot was deployed to the Koppel Bridge, the impact to the man hours showed a 34% reduction, while the expectation from the baseline was only 20%. The duration was also reduced by 34%. This was because the crew size remained the same and ended up placing the bars faster than they typically do, and they could devote more of their time to this activity as they did not have to tie the intersections. While those actual impacts are impressive, we extended our study to include how IronBot may impact the Koppel Bridge. Advanced Construction Robotics built and tested a full-scale prototype on its test bridge with a rebar design similar to that at Koppel to record actual productivity numbers. A commercially deployed version of IronBot will be out on a project by mid-2022. When IronBot is combined with TieBot on a project like Koppel, you get some amazing results. Over 400% productivity improvement of the workers. Remember the man-hour impact baseline number of 47% from our pre-study? The robotic team can increase this to 76% reduction of the man-hours. It does this by drastically increasing the placing capacity, reducing the schedule, and requiring less workers to perform the overall task. Cutting the duration by more than half and requiring 35% less workers are groundbreaking results. From the prior slides, it can be seen that construction robots are already offering great results to projects. There's still barriers, however, that exist that are preventing widespread adaptation. There's a misconception out there that robots will take jobs, when the reality is that robots will only help to make the workforce more productive. Many general contractors or specialty subcontractors don't want to try something new unless they absolutely have to, or they see how someone else has fared with it first. This is going to give early adapters a huge advantage over the laggards. As robotic technology penetrates the market, the costs vary depending on the project. The most common current end user is a specialty subcontractor who really needs to trade the technology dollars for those they save on their labor dollars. General contractors and owners will find value in completing projects faster with those utilizing robotic construction equipment. In best value projects, this can be very compelling. The most successful deployment of any new technology has buy-in from all the stakeholders affected, including the owners, trade unions, general contractors, and specialty subcontractors. Sometimes we find construction executives trying to implement the technology on a project, and there's resistance at the project level, leading to a difficult and unsupported deployment. Sometimes it is reversed, where the project level wants to try it, and the executives are too risk-averse, eventually killing a deal. The COVID-19 pandemic presented challenges for this technology, but also opportunities. When utilizing TieBot, there's a drastic reduction of worker density on the deck. With the IronBot and TieBot team, it will be even more severe, which is a good thing for social distancing. Overall, the three key benefits of improved safety, enhanced productivity, and reduced schedule all lead to the fourth benefit of increasing profits. Robots reduce workers' compensation exposure and offer a chance to preserve the long-term health of workers by lessening the physical demand on their bodies. The consistent and reliable output achieved by construction robots leads to amazing productivity improvements. As skilled labor becomes more and more scarce, this offers the option for performing the same work with less headcount if required. Anytime a project can be completed earlier, there's a huge benefit to the owner and contractor alike. As more and more robotic solutions are adapted to individual tasks, the more than half reduction in schedule can be very impactful. Thank you very much for your time. Please feel free to reach out to me to discuss how bringing robots to construction job sites can bring about positive results.